In this video, I would like to explain how to build the model for the example given in section 5.1 of the text, and the sketch is given in figure 5-4. I bring in the sketch here, so if you want to add a picture to your model, then click on the picture icon, and then click anywhere that you want to add the picture. And this is figure 5.4, and bring it into the, you may need to resize it and move it to make sure that it has the right size for your window. We are referencing to this sketch representing our mechanical system. So as you see here, we have two masses, mass 1, mass 2, and then associated with them spring and dampers, and mass 2 represent the driver and sitting on a seat of the car, and car floor has a moving up and down degree of freedom. We assume the velocities or displacement to be positive downward, as well as the gravity is acting downward. In addition to that, I would like to put a sign convention here, and to have it add a text to the screen. You click on the text symbol here, and then you type in what you want to add to the screen. Maybe I change the font to bold and maybe make it bigger so this is better visible, and then maybe also put a circle around it. So this is my sign convention. So what I mean by plus C means all the compression forces are taken to be positive. Obviously, tension forces are taken to be negative. The only force which is applied here is weight of these two masses, gravity due to gravity, and of course the signal is coming from the car floor when the car is moving on any signal that you want to represent the road or as an input to the car. Okay. So now what we would like to do, let's assume that you launch the 20 sim and everything is kind of not expanded. So you expand the bond graph, and then we have the tools in the bond graph for modeling this mechanical system. Now, the first thing that we should do, identify the distinct velocity. So these distinct velocities are associated with the mass 1, mass 2, and the floor. So we need 3 1 junctions. So we bring 3 1 junctions here. And then associated with each mass, I have inertia, so I need the I element. So I bring I element for this one and another I element for this one. Okay, so this is that. And also for the element, I need a flow source for the floor of the car. Now, in terms of the gravity, this is the effort which is fed into the mass 1 and mass 2. So we need effort source. I put them here for now. So these things will be connected to mass 1. Now, between the mass 1 and mass 2, we have 1 spring and 1 damper. So these guys will experience the relative displacement or velocity of mass 1 and mass 2. So I need a 0 junction here, because 0 junction is a flow summator, and then I need to sum up algebraically, of course, the velocities between these two. So I need a relative velocity. But we know that in a mechanical system, if we have parallel component like what we have here, the spring and damper, they experience the same displacement or velocity. When I say in bound graph, velocity and displacement are in terms of designation, we treat them the same. Of course, we know that velocity is derivative of displacement and so on. So when these two experience the same velocity, therefore this relative velocity should be shared with the one junction, and then this one junction should transfer these relative velocities to two components, which is R representing the damper and C representing the stiffness. The same thing applies here, so you can repeat the same. Sometimes it is useful to copy paste, but this is not a big model for now, so we can live with it. R and C, and of course another one junction I need to bring in to share the velocity. Okay, so this is that. Maybe I move this a little bit up so I can have some symmetry here. And basically that's it. Now, one thing that I would like to do, if this car floor was just, let's say, a wall, and then you had some maybe zero displacement or zero signal coming in, or maybe a constant displacement, then we didn't need to change it. But now I need to apply a signal here. For signal, I need a modulated flow source, MSF. So I replace this guy with an MSF, modulated signal. And once you have a modulated signal, you need a signal, because something should come here to be modulated, and that something is what you choose to. So we go to the signal section, and then I go to the sources. And for this example, I decided to use a step function. So I bring my step function here. I will assign the parameters of the step function later, but this is a generic step function here for now. And basically that's all the elements that I need for the bound graph model of this system. Again, we have three distinct velocities. We take into account their relative velocity with zero junction, and then pass these relative velocities to one junction and connect them to RC, the resistor and capacitor representing the damper and the spring. And also we need the gravity. So the gravity is a effort coming to the system. And there is a very important point about how to apply gravity in bound graph in general, and especially in 20C, that I will explain when I am connecting them. So remember that we take the displacement downward to be positive, and compression forces, internal forces, should be positives, should have a positive sign for compression. So that's all I need. Now I can move to connect these elements. If I don't connect them, they don't communicate to each other in terms of transferring the energy and interact and give me the dynamic representation of this mechanical system. So how do we connect? For connection, you have two ways. Actually, you can come here and then activate the connector, or you can simply press the space bar on your keyboard if you have. So either way is fine. So I just click and unclick, spacebar, activate, deactivate, or you can click here. Now, once I have this connector activated, the first thing that I will do, I will apply the connection from active sources. And if you get something like this, press the escape button and then do it again. So it should connect. And don't worry if it is red for now. If it is red at the end, then we have to take care of it. So for now it's okay. And another one here. And also the active flow, and of course coming from the signal. Now the next part that we do, we take care of the passive elements. Passive elements are those elements that receives power, like RCI in this case. They don't react to you. So if you put a, let's say, what is passive? So if you put a mass somewhere and don't apply any force to it, it doesn't do anything, right? Or a spring, if doesn't apply, you don't apply a force or a displacement, doesn't do anything. So you have to give energy or power to these elements. So that's why we call them passive. So this is passive again, this is passive, this is passive, and passive, and so that's it. Now, to have some visualization here, if I get rid of this connector for a second, see that there's a question how I am going to connect the remaining power bonds, and that is when this plus C comes into the picture. and of course the direction of your displacement in terms of coordinate system. So we have to connect them such that the bond graph representation is compatible with our assigned sign convention. So toggle again, and then I come here and connect the remaining. Sometimes maybe you have to move things a little bit to create some room for the bonds to be more visible, and that is fine. Especially when you have a big model, then this layout or architecture of your bond graph becomes more important. This model is relatively simple, 2 degrees of freedom, so we are good. Now, how do I check that my model complies with plus C? So take for example for a spring, for example, this K2. Which element basically represents this K2? This element C here. Because it takes the relative velocity between mass 2 and mass 1 and then communicate it to one junction and goes to C. So this is basically the velocity of the spring. So this velocity is coming from where? It's coming from this one minus this one, because we know that zero junction is an effort equalizer. So effort doesn't play any role here. So this is the flow coming to this junction minus the flow going out of this junction, which is transferred to this. So this is very obvious if you write the power balance for this zero junction, as I explained in the text. Now, if this one minus this one wants to be positive, which is the displacement of the spring here, therefore this flow should be larger than this, meaning that the displacement or velocity of mass 2 should be larger than mass 1. That means that it puts the spring under compression, and that is exactly what I want. So these things are moving here. For example, this is moving, say, 3 centimeters. This cannot move more than 3 centimeters, should be less. Therefore, this spring is under compression. And obviously, in the opposite, it is tension, which is negative. So this takes care of that one. Now, if I come here and look at the SE, SE is a effort source. So which is representing my gravity. If the gravity is matching, the direction of the gravity matches the assigned coordinate system, which we have it here, both of them are downward, g and x's, x1 and x2 are downward. Therefore, the gravity feeds power into the system. Otherwise, the system should do some work to go against the gravity. So in that case, it is taking energy from the system. Now, and if I am going to draw these things by hand, and my x1 and x2 direction are upward, therefore I will reverse this direction for the power bond. I will get the half arrow from 1 to SE. But in PLC we cannot do that, but you can do it by assigning a negative value to G. So bottom line, if your G and X's are matching, give a positive value to SE, and if they are opposite, give a negative value. Okay, so once you reach to this point that you have all of your power bonds connected, and then you see the causality strokes are automatically assigned, and we see unicolor for the causality strokes. So everything is good, everything is integrally causal, shall we say, especially the I and C, as we discussed in the text about the causality. And this is a very important part of bond graph, but one of the advantage of this tool is that it is automatically assigned. If you see for your model that one of your causality strokes are not in black or the same color as the rest of them, usually it comes in green or some color close to the red, or some color close to the red. Therefore, you don't have for that bond graph an integral causality. It's not end of the world, but we have discussed in the text that it could be algebraic loop or derivative causality, and you will get the in the message underneath here. Now, once you reach to this point, you would like to see if your model is complete and there is no bug here. So this is the tool here. So you go and double click here, and you see under the model some information that the model has 0 errors and 0 warning. This is very good. I have 10 submodels, 17 equations, 13 variables, but actually 4 independent state variables. And this is very important to realize that why I have 4 state variables. And as I discussed in the text, the state variables are associated with the momentum of the masses and the displacement of the spring. So I have my state variable will be in terms of the momentum of mass 1 and mass 2 and two springs. So that's why we have 4 independent state equations. But the main thing that we are interested here, we have 0 errors and 0 warning. Now, if you are interested to see actually the equation, you can go to model and say show equation, and here we go. So these are the static equation, and these are all the equations, and this piece is the state equation, as I mentioned. So if you look at here, you know, we have state the momentum of I, which is this guy, and momentum of I1, which is this guy, mass 2 and mass 1. And so these are two equations, and also state of C and C1, which is the displacement for the spring. So that's why we have 4 equations. So through some manipulation, the software goes and eliminate the rest and gives you a system of 4 equations, and then you can solve it for this model. Now, you can also, and I have explained in the text, for small systems, not very complex, it is possible to extract the equation, system equation, using the bound graph model here by hand. But practically, when the system gets very complex, it is not a good way of doing it, but we will do it for some small example to show you that it is possible to do it. So in another way, this TwinSim is a very useful tool, so you can actually do practical design using this tool, and of course, after having your bound graph model. Okay, so we have our model ready. The next thing that you may want to do is to go back and actually change the name of each element, the bound graph element. For example, if you want to change this represent mass 2, so you right click on I and go to properties and say mass 2. So therefore you get this name here, mass 2, and you see here that mass 2 actually represents its physical system method. That's a good thing to do. That's optional. It's not required for running a model, but it is highly recommended, especially when your system becomes more complex. So we will change these values and so on and so forth. So this is part 1 of this demonstration video. In part 2, I will show you how to actually assign values to these parameters, give values. So when you want to design a system like this, for example, you are responsible to design the seat and you want to make sure that the driver doesn't experience, based on the signal that you are giving to the car floor, doesn't experience a sharp velocity change or a defined range of displacement. Also, these are the design objectives. So you need some numerical values to be assigned to these parameters, masses and spring and dampers, and of course giving the I chose the steps function, but you can actually have a function taken from the field or some standard function applied to the car seat. So in second video, I will explain how to assign the numerical values to the parameters, and we will go to some of the equation model of these elements and make sure that everything is according to what we want to be. Okay, so this is part 1. In part 2, we will do that.